Today we're going to talk about buffers. Buffers, and we're going to describe buffers, and we'll work out some math problems about buffers. But the neat thing about buffers is you have these within your body. Some of you, did anybody get a juice in here? Orange juice or citrusy type of juice? Or anybody have orange juice this morning? Good, there. Citrus is what, acidic or basic? Typically. Acidic. So what that will do is you're adding an acid to your bloodstream by ingesting orange juice, and it should cause your blood pH to go down. In other words, as you add an acid to a solution, the pH should go down. Well, buffers help to absorb those extra hydrogens or hydroxides, and it doesn't matter if you're adding an acid or a base to the solution, it helps maintain that pH. So when we talk about buffers, the term there at the top says, the term buffer or buffered solution is usually describes a buffered solution, which is a solution that resists change to pH when an acid or a base is added. So it doesn't matter if we're adding an acid or a base. Now when we talk about adding an acid or a base, what we really want to talk about is adding hydrogen or hydroxides. And typically what we'll be doing is we'll be adding a strong acid or a strong base to our solution. So when these things break apart, and that's one reason why we want to know our strongs, if we're adding a hydrogen ion or a hydroxide ion to a solution, it will cause the pH to change significantly if there's not something there to absorb the hydrogen or hydroxide. So today when we talk about buffers, we're going to talk about how we can, quote unquote, maintain the concentration of hydrogen or hydroxide and don't let it exceed. There isn't a limit to a buffer, okay? So you just can't keep adding a acid or a base, but if you add a certain amount, it'll be able to handle it. Now, what the statement says, it helps resist a change in pH. And when we work out some of these problems, if we look at just the acid alone or the base alone, it could be on the extreme ends of the pH scale. So it'll help maintain that. Later on down, about the fourth line, it says the amount of acid or base that a buffered solution can handle before it's changing to any appreciable level is known as the buffer capacity. So when you hear me talk about, okay, we added way too much acid or way too much base, and we exceeded the buffer capacity. So the pH now is going to go, if I'm adding an acid, it's really going to drop. Or if I add a base, it's really going to elevate. So there are certain systems that don't want you to exceed that. But if you keep adding it, it's going to cause the system to go very, very basic or very, very acidic. Okay. Let's work out some of the examples on the front page here. Example 1, part 1, says a buffered solution at equilibrium contains 0.75 molarity acetic acid, which has a Ka value of 1.8 times 10 to the negative 5, and 0.75 molar sodium acetate. I want you to calculate the pH of this solution. Now what's really nice about this is the same type of stuff that we've been doing or we did on the last quiz. So let's go ahead and start with the salt first. So we've got sodium acetate, and recognizing that that is a salt, that's really helpful because we know that the salts dissociate completely, form sodium and the acetate. So again, the Na is not going to do anything since it's a conjugate of a strong base. However, this is acetate, which is a conjugate of a weak acid. So when we make our ice chart, actually what's really neat about this, it says that it's giving us our concentrations at equilibrium. So we can write out our equation. Okay, since we have acetic acid, it'll form hydrogen ions and the acetate. Okay. And what's nice is it gave us the concentrations at equilibrium. So if it says the concentrations at equilibrium, we don't need to do the 3 steps in the ice chart. Just go right for E. So in this case here, we have our concentration for the acetic acid at 0.75. Since we're at equilibrium, we're actually going to look for the concentration for the hydrogen. It's not 0 because it's at equilibrium, so there is a value there. Because we're looking for the pH, we want to find out what that is. And also, for this salt here, we were given a 0.75 molarity for that. So when that dissociates, this is 0.75 molarity. Okay. All right. Since we have our conditions at equilibrium, now we're ready for our expression. So go ahead and write your expression. And since we have hydrogen, we want a Ka value. So hydrogen times your acetate, the C2H3O2, over your acetic acid. Okay. And the Ka value was given as 1.8 times 10 to the negative 5. Okay, so we can go ahead and plug in those values. So we're looking for the hydrogen concentration. We know that we have a 0.75 molar solution of acetate. And since it's at equilibrium, no plus X, no minus X, since that is our equilibrium concentration. Also, based on the question here, we have a 0.75 concentration for our acetic acid. What's really nice, you don't need a calculator to find out what your hydrogen concentration is. So the 0.75s cancel out, your hydrogen's equal to your 1.8 times 10 to the negative 5. So to find your pH, again, just like what we've been doing, take the negative log of that value. So hydrogen, so negative log of 1.8 times 10 to the negative 5. So 4.74 is your pH. And that's the pH for our buffer solution. Now, what's really neat about this is we have a concentration for our weak acid and for its common ion, or the conjugate of this weak acid, which is acting like a base. So this is our buffer solution, and our pH is 4.74. Now, as you do or work with more and more of these buffers, I didn't have to start with hydrogen here, okay? The nice thing about acid and base buffer solutions is that when we look at these things, a buffer can handle either hydrogen or hydroxide. So even though I went ahead and had the acid on this side and the acetate on this side, I could flip this and write it so that the hydroxide is in here. If I choose to do that, and hydroxide is always on the product side, so I have OH here, and since I have OH, I have to have water, because that's where we're getting the OH from. So instead of having the acetic acid on this side, I'm actually going to have my acetate on this side, and then my weak acid over here. Okay. So this is another way that you could write out the problem. And again, we had our concentrations at equilibrium, so 0.75 dash 0.75, and this would be what we would solve for. Now, the only time that we would want to do this or even consider this is if we knew that we were going to add a strong base in the next step. So it's probably not a bad idea to read ahead, but if you want to, you can go right ahead and go right in for the hydrogen here if you're not sure if it's going to be adding a strong acid or a strong base. However, do realize this, it does change your expression, so you would have to have a Kb expression because you have hydroxide, so you would need to find out what the value for this was. And you would have to do this in this step or in the following step regardless, because it is a hydroxide. So you'd find the Kb value, you'd also write the expression for that. Part 2 says calculate the change in pH that occurs when 0.01 mole of gaseous hydrochloric acid is added to the 1 liter solution, this 1 liter buffered solution. Compare the above pH with the pH of the hydrochloric acid. Okay. Now, we can do this. We know that hydrochloric acid is what? Strong, very strong. So if I have, what is it, 0.01 mole? if I have 0.01 mole of hydrochloric acid, and what was my volume for this? 1 liter, right? So my molarity is 0.01. What is the pH of just hydrochloric acid in this case? Well, if you wanted to find out, we know that hydrochloric is strong, so it'd break apart into hydrogen ions. And if I wanted to find the pH of just this solution right here, I take the negative log of my hydrogen concentration, which is 0.01. And that equals 2. Okay? And that's a big change in pH, going from 4.74 to 2. It's almost a change of 3. If I didn't have a buffer solution. In other words, if I just added that hydrochloric acid to pure water, this is what my pH of the solution would be. All right? So what's going to happen is this buffer is going to take all these hydrogen ions and try to keep them under check so it doesn't deviate too far away from the 4.74. So knowing that the pH, actually let me just put alone here, is equal to 2.0. Okay, let's see how, much our buffer will handle. Okay, so here's what we want to do. Since we know that we're adding hydrogen to this solution, I want to leave my ice chart the same way. Okay, it's going to look like this. Okay, so that's one way to write this ice chart. If I'm adding an acid, a strong acid, and what's really cool is whenever we add something to a buffered solution, it'll either be a strong acid or a strong base. There's no weaks here. Okay, we know that we had 0.75 molar as our initial concentration, and I do want to do a full ice on this one as our initial. We had 0.75 for this one as well, and what did I say the concentration for this was? 0.01. Okay. Now, you may not use the 5% rule for this. You don't need to. Here's what you need to do. After we've added these in, there's no Le Chatelier. Okay. We're going to look at how this system is going to handle the excess hydrogen or hydroxide. Ideally, we want the hydrogen or the hydroxide, depending on if we're adding a strong acid or strong base, to be less than the thing that it's actually reacting with. And in this case, that's good. We can say that this is an okay buffer solution. We don't know if it's a good one yet because we want to see what the change of pH is going to be. But we want to make sure that our hydrogen concentration is lower than our common ion or acid that this is reacting with. And in this case, it actually is. So whichever of these two values is the smallest, that one will be X. Okay? We'll never say that hydrogen or hydroxide is always X. Oftentimes it should be, but it doesn't necessarily mean that. So whichever of these two values is smallest, that's what's going to happen. Because here's what's going to happen. Once I add this hydrogen ion or hydrochloric acid to the solution, for it to maintain a close pH, the acetate is going to jump on this hydrogen to make acetic acid. That's how we take the hydrogen ions out of solution. Because the higher the concentration of hydrogen, the lower our pH will be. And we want to maintain a relatively level amount. So we'll reduce it on this side while adding it to this side. So if I subtract on one side, I add to the other. So this will go to 0, and then equilibrium will reestablish. So I'm going to put approximately 0 because we don't know how much. That's actually what we're going to calculate. And then this will be reduced to 0.74, and this will be increased to 0.76. Again, our values at equilibrium, we're going to plug that back into our expression as long as we have hydrogen. So since we have hydrogen here, we have a Ka value. Now you don't have to rewrite this if you did it in an earlier step, but I already erased it, so that's wonderful. Oop, not 2. Okay, so we have, essentially we're looking for the hydrogen, and we have 0.74 over 0.75, and it's still equal to Ka, so I have 1.8. I should have wrote that out. So that's going to go up. We're going to divide that. So now our hydrogen concentration will be 1.8 -5 times 0.76. So around 1.8486, and I don't want to round this too much just yet, times 10 to the -5. So that's my hydrogen concentration. Find the pH. Take the negative log of my hydrogen concentration. So whatever's in my calculator, and don't round, because if you round then it goes back to what we had before. So negative log of the answer, 4.74. So 3. Okay. So this was a pretty good buffer. I mean, we added what I would consider a significant amount of hydrochloric acid to the solution. And had it just been water, the pH would have been 2. However, since we had a buffered solution and was able to absorb quite a bit of that hydrogen, the pH only changed by 100th. So it went from 4.74 to 4.73. Trust me, if your blood pH was this and then it went to 2, you're dead. Okay? If it changes by 2, it's not going to be good. All right, so this is I would say this is a very nice buffer solution. And it did not exceed the buffer capacity because this amount was not greater than this. Now, also what we could have done, okay, this is our situation with hydrogen. We could have also added a base to this solution. Now, it's not part of our question here, but I want to show you how this could have handled it. Because a buffer solution can handle either an acid or a base. So since we have the acetic acid and we're adding hydroxide, the way this would look is we always want to make sure that our hydroxide or our hydrogen is on the product side, and that's a really important point. Hydrogen or hydroxide must be on the product side. Okay? And we're going to flip the equation. So if we had the hydrogen reacting with the common ion to form acetic acid, we would have hydroxide reacting with the acid. So in this case here, we'll have our, and on the other side, we would have our C2H3O2 and water. Okay? And again, we always want to make sure the equation's balanced. So if I would have been adding a strong base to the solution, here's how the mechanism would have worked. The hydrogen from the weak acid would have attached itself to the hydroxide, forming water, and leaving this alone. So again, as long as our hydroxide or our hydrogen concentration is not greater than the thing that it's reacting with, this is a pretty good buffer. Okay? All right. Now on the back side of that first sheet, it goes through how does a buffer work. I think I already went through all of that. Okay? And we'll have some more practice here. All right. On the second sheet, it says a summary of the most important characteristics of a buffered solution. First bullet there. Buffered solutions contain relatively large concentrations of a weak acid and its corresponding base. Okay? So getting back to our problem here, these are high concentrations compared to our strong acid or strong base. Okay? We want to make sure that we have significant values here to be able to handle whether we're adding a strong acid or a strong base. Second bullet, when hydrogen ions are added to the solution, it reacts essentially to completion of the weak base present. Okay? Technically, this would be considered the weak base. It's a conjugate of a weak acid. So what's going to happen is the hydrogen is going to jump on this to form the acetic acid. And then in the reverse direction, that's what the third bullet's saying, is that when we add hydroxide or a strong base to this, it'll react to the weak acid to form the common ion and water. So what we're trying to do is we're trying to eliminate the hydroxide or the hydrogen ions, because these are the things that cause the pH to change. It's not these. These don't do anything to pH. its hydrogen or hydroxide concentration. And then the fourth bullet, the pH in a buffered solution is determined by the ratio of the concentration of the weak acid and the weak base. As long as the ratio remains virtually constant, the pH will remain virtually constant. This will be the case as long as the concentrations of the buffering materials of the weak acid and its common anion, or the base and its, in this case, the base and its weak acid, are large compared to the amounts of hydrogen or hydroxide added. All right, let's do another practice problem here. It says a buffered solution at equilibrium contains 2.55 molar benzoic acid, and its Ka value is given, and 1.37 molar potassium benzenate. And I want you to calculate the pH of this solution. So we're always going to find out what the pH of the buffered solution is to see if it's the type of solution that we want to have, first of all. So let's see here. We've got, let's go ahead and take care of the potassium benzenate first. So what is potassium benzenate? What is that, an acid or a base? It's a salt, very good. Because we're going to dissociate it. So what's the potassium going to do to this? Nothing. Absolutely nothing. So it's a spectator. That was part of our quiz. So this will cause the solution to become basic if it's the only thing placed in the solution. So this acts like a base. So we have our benzoic acid. Okay. Okay, so there's our equation. We have a 2.5 molar solution. And again, since it's at equilibrium, we don't know how much hydrogen we have, but we're adding the salt to this, and we have 1.37. I'm just going to go ahead and go with at E so we can find out what the concentration is. Because it doesn't change, we're using 5% rule, and it'll help speed things up. So we want to write our expression. So is this a Ka or a Kb? Ka, because we have hydrogen. So hydrogen top, the benzenate. So we're looking for the hydrogen concentration. We have 1.37. That's equal to 6.52 times 10 to the negative 5. Okay, so we're going to bring those up, bring that down. So our hydrogen concentration is 6.52 times 10 to the negative 5. And 1.37. Okay. So 1.21 times 10 to the negative, what is that, 4? Okay, so that's my hydrogen concentration, so we can find out what the pH is. Again. So 3.92. Anybody get that? All right. So there's our buffer. Has a pH of 3.92. Okay. Part B says, all right, now calculate the pH, or calculate the change in pH that occurs when 0.85 moles of solid sodium hydroxide is added to 1 liter of this solution, of the buffered solution. And then it says, assume that the volume change is negligible here, and it'll always be that way. What do you think is going to happen if we add a base to this? Will the pH go up or down? It's at 3.92. Should it go up or down as a result of adding a base? Should go up. So if I just added that base to the solution, we can find out what the pH would be. Actually, let's do that. So it's 0.85. So sodium hydroxide, again, strong base, dissociates completely. And we have a 0.85 molar solution because we have 0.85 moles in that 1 liter. So the hydroxide concentration is equal to that value. So if I take the negative log of that, actually I'm going to take 14 minus the negative log of that, because this would be my POH. That would give me a pH around 13.92 if I place that in pure water. So that's a big, big jump, okay? That's ridiculous, actually. So if I'm going to add this sodium hydroxide to my solution, I definitely don't want to write my ice chart like this. I need to add the sodium hydroxide in a way that the system can absorb it. So if you add a base, then we want to react it with our, oops, not on that side, always wants to be on the product side. If we add a base, we want to make sure that it reacts with the weak acid. So in this case, so the hydroxide or hydrogen will always be on the product side. Because, again, the reason why in our K expression, we always want it on top, products over reactants. And then we'll have our benzenate on this side, plus water. And do show the water. Okay? You have to show the water. We have to make sure that we have the same number of atoms on both sides. So we have our, and don't mess up the numbers, 1.37 there, dash 2.55 here. And we said that our hydroxide was 0.85. Okay. Again, whichever value is the smallest goes to 0. That is our X. Again, don't get in the habit of saying, oh, whatever my hydrogen or hydroxide is. Because I promise, I'll give you a problem where these numbers might be flip-flopped. I might give you like 2.55 here and 0.85. Then the problem becomes very easy. I'm not going to tell you how, but it becomes very easy. So whichever value on the product side is smaller goes to 0. And then we'll add it to this side. So it does go to 0, and then it reestablishes equilibrium. So that's what we're going to solve for. Okay. So 1.70 here, and 2.22 over here. Okay, so there's our concentrations. So once we have that, are we going to write a Ka or a Kb? Okay, what? Kb, very good. So since we have hydroxide, you have to have a Kb expression. And some of you didn't do that on the quiz either. Bad. Okay. And there is no 5% rule, so we don't have to drop any X's or add any X's, because we know what X is if you add a strong to it. 2.22. Now, do we know the Kb value? No, so we got to find it. So Kw over Ka over, what was it, 6.52, 10 to the negative 5. So 1.53 times 10 to the negative 10. Okay. So multiply that, divide by that to get our hydroxide. So 1.53. Over 1.70. So 2.0 times 10 to the negative 10. So to find pH, 14 minus the negative log of your hydroxide, so 2.0, oops, times 10 to the negative 10. Yawns. 4.30. Okay, so not bad. I mean, it's a little bit bigger change than our last example, but that is definitely keeping it in check from changing to 13.92. Do realize that this solution is still considered to be what? Acidic or basic? Acidic, because we're below 7. If I just had just hydroxide in the solution, it'd be really basic. Okay? So going from 3.92 to 4.3, not too bad. That really kept A from going to a basic side of the solution here. All right. Now, some of you probably love showing all this work, right? You enjoy that, all this effort and energy. I asked you guys to get your equation sheet out. On the back side of the second example, there's a little formula on here, and it's located on your equation sheet just above, it's about the fourth and third from the bottom. Okay, this is what's called the Henderson-Hasselbalch equation. And if you know how to use it, I don't mind you using it. If you don't know how to use it, you need to be showing me all of this. Okay? I'll explain what the Henderson-Hasselbalch equation is. I'm going to leave this up here. I'm going to erase this over here. Actually, no. Yeah, I'll leave that up. That's fine. No, I'll do this one. Okay. Henderson-Hasselbalch equation is kind of a neat little equation where it helps speed things up. But again, you don't have to use it if you don't want to. In this problem here, I want you to notice something. We have hydroxide, right? But what are we looking for? The pH of the solution. The Henderson-Hasselbalch equation for pH is this, where we have pH is equal to the, is it negative pKa? No, it's regular. pKa plus log of A minus over HA. Now, this is where most people have issues, because they can't keep the HA and the A in check. What I want you to recognize, this part right here, okay? Who's my HA in all this? Does anybody have any idea? In other words, it's asking for the weak acid. Right here, right? This is my HA, and this would be my A minus. If you know the concentration at equilibrium, okay? Okay. So we'd have our value for HA right here at equilibrium, not initial. We never care about anything initially. We only care at equilibrium. And our anion concentration at equilibrium, we can plug those two values in and just take that divided by that and then take the log of that. pKa, remember when I talked about P? What does P mean again? In other words, when we talk about pH and pOH. pH and pOH. What did P represent here? It's a log function, okay? In other words, it's saying it's the negative log of the hydrogen concentration. For here, it's the negative log of the hydroxide concentration. So if I see pKa, it's a negative log function of my Ka value. Okay? That's what P stands for. It's a negative log function. So we can put the P in front of that, and so we can just find the negative log of my Ka value. And what's really neat, what did I have to do on this problem here? I had to find the Kb because I had hydroxide. Even though I have hydroxide in this problem, I can still use this because it doesn't ever ask for hydrogen or hydroxide concentration. All it cares about is my weak acid and its common ion. If you have a Ka value, which was given in the problem, okay, we can just go right for it. So we can do pH is equal to the negative log of our Ka, which is 6.52 times 10 to the negative 5, okay, plus the log of our concentration of the anion over our weak acid. So that's why I had the ice chart, and you must show an ice chart for buffers. Okay, so the 2.22 divided by the 1.7. Do this first before you hit the log button. Okay, so really it looks more like that. If you type it in correctly, I'll bet you it equals that. It's up to you. If you're comfortable with this, continue. If you know what you're doing, you may do this, okay? The key here is you have to show your process. Don't just give me a number that your calculator spit out. I want to see what you're doing. So you got it. You always have to show the ice chart for buffers. Once you add that strong, you've got to show this, because we need to see what the X is equal to, because there's no 5% rule. And then once our concentration's here, I would do this. I would write HA and A minus above, just to keep your butt out of trouble. Okay? Even though we're adding hydroxide to this solution, this equation does not care. Okay? And then if you look at the other equation where it's looking for POH, and unfortunately we don't ask for POH very often, but it's similar, where POH is equal to the PKB, okay, and then it's plus log, is it H on top? I can't remember that one. I don't use that one very often. HB on top, or what I have you guys write is BH for your B, okay? So you have to know which is which here. If you want to use this for this problem, that's okay, because you can. The key here is recognizing that this has one more hydrogen than this. So who's my base in this problem? We know this is a weak acid, that's the anion. Who would be the base in this problem, or this ice chart? The one on the left or the one on the right? Right here, that's your base. Because this has one more hydrogen than this. So that's your BH, or your HB, however you want to do it. So if you know those values at equilibrium, plug them in. Of course, you have to know your KB, and hopefully that would be given to you where you wouldn't have to calculate it. Okay? So these two equations are there if you wish to use them. If you're not comfortable with them, and you still want to do this, you'll have plenty of time to show all the steps for this. Okay?